Yeah, thank you very much. Thank you for inviting me. It's a great honor to be here and to speak here. Yeah, so the topic of this talk is the computational complexity of constraint satisfaction problems and how countably categorical structures show up there as basically as a tool to analyze the computational complexity. So let me start with the basic definition of a constraint satisfaction problem. So it's a computational. These are computational problems in theoretical computer science. And what we do is we fix a structure gamma, which has a finite relational signature. Yeah? The structure can be infinite, but we have a finite number of relations defined on the structure. And typically, if we use it for constraint satisfaction, the structure gamma, we call it a template. And now the computational problem I'm interested in is the CSP of gamma. So we are given and you should. Yeah, it's a finite structure that has the same signature as our structure gamma. And the question is there a homomorphism, yes or no, to the structure gamma? It's a decision problem. Let's look at an example. If we fix gamma to be the clique with 3 elements, K3, then what does it mean to have a homomorphism from a structure with the same signature? A structure with the same signature is just a graph. And we are interested in homomorphisms, so we don't want that 2 adjacent vertices in G are mapped to the same element in K3 because there's no self-loop. So in other words, we don't want that adjacent vertices in G get the same color. So we want a 3 coloring. It's just a 3 coloring problem. CSP of K3 is 3 colorability. Now we look at, I already mentioned the structure gamma can be infinite. How would we model this computational problem as a CSP? So what is this problem? We are given this time a directed graph. And we would like to know, is it acyclic, yes or no? And well, there are many templates that you could pick. But one nice template that we all love is Q with the order. And it's clear if there's a homomorphism to Q, there's no cycle. And vice versa, if there's no cycle in your graph, you can certainly homomorphically map it to Q. And this is an easy problem. It's in P. You can decide it efficiently. But, now, slight variation. Here, we are again, we are interested in the following computational problem. This time, the input consists of triples, x, y, z. And we would like to assign values to those variables such that for each given triple, the middle element, y, is in the middle with respect to the assignment, right? The betweenness. And this is called the betweenness problem in theoretical computer science. It's now straightforward to pick the right template. We just pick again Q and choose the right ternary relation so that the homomorphism problem for this template is precisely this betweenness problem, which is very famous in theoretical computer science, many papers about it. All right, these examples I use very often in talks because they are so simple. But I also like to show you an example, which is, well, I think I've never used it in a talk, just to demonstrate, so it's called RCC8, just to demonstrate that people in computer science, they very often work with computational problems. And in fact, they are CSPs for some nice, homogeneous, wonderful structure without even noticing it very often. Yeah? So, and I want to go through this. So this is actually an artificial intelligence where people are, they are interested in qualitative spatial reasoning. That's what they call it. And they're really interested in building robots that make common sense inferences. And so they devised the following formalism. So they want to talk about regions and their relationships in space. So they distinguish the following 8 relations. Little funny names. It's not my names. Yeah? It's the names they use. It's standard. So X dcy means that well, PO means proper overlap. So these 2 regions, they properly overlap. These 2 regions, they don't properly overlap because their interior is still disjoint. And yeah, so they have these 8 relations. That these regions can be contained in each other. These are the exhaustive list of binary relations they want to treat. And all right, so formally, what is this formally? Formally, they just have these 8 relations. They require that for every xy, precisely one of those relations holds. And then they have a set of axioms. I don't want to read this out, but it's actually very silly. So these are just two shortcuts. They define two shortcuts. And this, for instance, I will read out only one that you see how simple this is. If x and y are disjoint and y is contained in z, then x and z are, no, z is contained in y, sorry, then x and z are still disjoint. Things like that, yeah. Yeah? Yeah, our topological space, and you have some, right, you have some notion of interior, yeah, so it's basically, you can imagine as some topological space. Right. That's where the intuition comes from, but formally what they do at the end, yeah, and formally what they do at the end is they just write down these axioms and say this is the formalism. But the intuition clearly comes from you have this topological space there. All right, but now what is the relation to the CSP? Yeah? So actually you can verify that if you look at finite structures with these 8 relations, satisfying those axioms, it's an amalgamation class. No? You have to verify this, but it can be done. And so yeah, let's look at the Freisel limit. And if you look at the CSP of this Freisel limit, it's precisely the most studied computational problem for RCC8. It's the problem they are actually interested in. They've studied a lot, constraint propagation for it. It can be solved in polynomial time. Just to indicate you how these structures arise naturally, actually, for those problems. All right, another example, this will be the last example, because also it's a very nice homogeneous structure underlying it, Borrown trees. So let's look at finite trees. Now, trees are different here now than the trees we've seen before. Now it's really trees in a graph theoretic sense. It's connected graphs without cycles, finite. Right. But I want that they only have degree 1, that all vertices have degree 1 or 3. Now, there's a different way to represent those trees. You can use a 4-array relation. And I want that this relation holds on x, y, u, v if the shortest path from x to y does not intersect the shortest path from u to v. Right? Again, you can verify that, well, no, first of all, I'm now looking at structures, finite structures, where the domain is just the vertices of degree 1, yeah, not the internal vertices. And I put this relation on them just as I described. Yeah? Right? And you can, again, verify that this will give a Freisel class. It's closed under taking substructures. It has the amalgamation property. So let's look at the Freisel limit. And it's precisely the CSP, what people in phylogenetic analysis called the quartet consistency problem. Right? So again, there are many papers about this problem, but without any connection to this very nice structure which has been studied independently, or clearly. And it's NP complete. Right? It's a difficult problem. All right. So what will be the topic of this talk? So I'm given a structure gamma, and I want to read off from the structure gamma what is the computational complexity of the CSP. I would like to have a mathematical theory which tells me for which, say, homogeneous omega categorical structures gamma, this becomes easy, and when is it NP hard, say. And let's start with a simple setting. Let's look first at the situation where gamma is finite. So this is very restricted. So none of the examples we have seen before can be formulated when gamma is forced to be finite, except for the K3, free colorability. None of them can. But already, if gamma is finite, this classification problem is open. So, and there's a famous conjecture which stimulated a lot of research activity around here. It's the conjecture of Federawardi. They conjecture that for all finite structures gamma, this problem is either in P or NP complete, and this is still open. But most people believe it. So, and it's true for many special cases. So this has been called a dichotomy, complexity dichotomy, and it's true for 2-element structures. This is a classical result in Boolean satisfiability. It's true for 3-element structures, more recently by Bulatov. It's true if you play with the signature. If you force your structure to be a graph, an undirected simple graph, then Helen Neshetrill, they proved that the dichotomy is true as well. So for any fixed gamma, which is a graph, finite, the CSP for it is either in P or in P complete. More recently, digraphs without sources and sinks. So there are many, many positive results, but it's still open for digraphs in general. And it's as hard, actually, as the full classification if you can solve it for digraphs. It's also open already for 5 elements. We don't know how to prove this for 5 element structures. All right. So why do people? I mean, if you can already prove, if you're not able to prove it for 5 elements, why do people believe in it still? And the strongest evidence comes from something that has been called the universal algebraic approach. And I will now introduce the universal algebraic approach. A brief introduction to this. Why do people believe that this is true? So, but first, what is the proper scope of this universal algebraic approach? Actually, there's not so much special about finite structures for this approach. So the right setting to actually study this approach is the much wider class of all omega categorical structures. That's the right setting. And well, the definition, you know, a first order theory is omega categorical if all countable models of the theory are isomorphic. And a structure is omega categorical if its first order theory is omega categorical. So in particular, finite structures don't have countable models of their first order theory, so this really generalizes the class of finite templates. But also all the templates that we have seen earlier. Yeah, these were Freisel limits in a signature which is relational and it's a finite relational signature. So these Freisel limits will also be omega categorical. Why? One way to see this is via the theorem of Ril-Nachevsky. That's like if and only if characterization of omega categoricity in terms of the permutation group of odd gamma. So a structure is omega categorical if and only if the action, the natural action of the automorphism group on the n tuples is oligomorphic, has finitely many orbits for all n. All right. And there's a systematic way of producing, as we have seen already in 2 examples, of producing omega categorical structures via Freisel limits. So now what is the remainder of the talk? So as I said, I will introduce this universal algebraic approach, give an introduction to it, and this actually can be decomposed into 5 steps, this approach. 5 important steps, and then I will present some classification results that have been obtained by this method for omega categorical structures. And there, and this will be, I think, a link to many other talks or a topic of this workshop. An important tool to get those classification results is Ramsey theory. So we use Ramsey classes to do the combinatorial analysis that is necessary in this classification. And there are some open problems. This has triggered some open problems that are of interest. I've seen in Lionel's Fante's talk and I'll close with open problems. All right. So the first step of the universal algebraic approach. It's the notion of primitive positive definability. So we have a first order formula. We say it's primitive positive if it's very simple. It's just a conjunction of atomic formulas. And then I'm allowed to existentially quantify some of the variables. All right. So there's no universal quantification, no negation, no disjunction. It's forbidden. So now you might say, oh, this is horrible. I need negation. Or is this an interesting concept? It's too simple. But it's definitely a nice concept. And it's definitely complicated sometimes to decide whether something can be defined primitively positively. In some sense, you can view the book of Matyasiewicz as a single primitive positive definition. Yeah? It's, I mean, the main missing step of Matyasiewicz's theorem was the fact that the exponential is definable primitively positively over set. Yeah? It can be done. All right. So why am I interested in primitive positive definitions? It's a very simple fact, but very powerful, that if you have a structure gamma, and you add a relation to it that is primitively positively definable over gamma, it will not change the complexity of the corresponding CSPs. A priori, the CSP where you add a relation R, which is primitive, it could be more difficult. Yeah? You add more expressive power. But since it's primitively positively definable, you can simulate it with your templates introducing new variables. So this is not very surprising. So this is the right concept we're interested in for the CSP because it preserves complexity. So the central question is now, how do we recognize whether a certain structure, a certain relation R is primitively positively definable in some given omega categorical, say, structure gamma? And for this, there's a very nice tool. So I need some standard notions. A function, which might be k-ary, a function from d to the k to d, preserves a relation, an m-ary relation, if, when you apply f component-wise to the tuples from the relation, you get back a tuple in the relation. If a function preserves all relations in a structure, you say it's a polymorphism of this structure. And polymorphisms generalize automorphisms, obviously. Yeah? So the set of all polymorphisms, that is a sort of a more powerful object than the set of all automorphisms. And another way to look at polymorphisms is you take a direct product of your structure and you look at homomorphisms back into your structure. And well, what is the link to primitive positive definability? If gamma is omega categorical, finite or countably infinite, omega categorical, then a relation R has a primitive positive definition in gamma if and only if it's preserved by all polymorphisms. One direction is simple. Primitive positive formulas are preserved by polymorphisms. But the other direction is more. It has been known for finite structures since a long time. And with Jarek, we proved it that this goes through for omega category. It's not terribly difficult, but it's very powerful. It's very powerful because these sets of polymorphisms form algebraically very nice objects. They are. So the set of all polymorphisms is closed under compositions. You compose polymorphisms, you get back polymorphisms. And they always obviously contain the projections. And those objects, sets of functions that are closed with under these two things, are called function clones in universal algebra and are studied there. Mostly for finite domains, but also for infinite domains. Okay. This was the second step, right? Polymorphisms. The third step is cores. So this has been very important for finite structures, gamma, this concept. And it smoothly goes through for omega categorical structures as well. So you just have to do the right definitions. A structure is called a core if all endomorphisms of the structure are embeddings. Now, for finite structures, very often you see automorphisms, but of course it's equivalent. For infinite structures, omega categorical structures is no longer equivalent, whether you write automorphisms or embeddings here, clearly. And you should write embeddings. That's the fruitful generalization. Just an example, this structure is not a core. It's a finite graph. You can, for instance, map this vertex. You can map it, this vertex, you can map it here and fix those three, and this you can map here. It's not a core. This structure, the K3, is a core. And we have a homomorphism from here to here and from here to here. So they are homomorphically equivalent, those two structures. Now, there's for the model theorists here, there's sort of something that feels similar. Yeah? So model theorists, they call a theory T model complete if embeddings between models of T preserve first-order formulas. So why should that be related? Well, look at an omega categorical structure. There you only have one countable model. So actually, homomorphisms between models become endomorphisms. And embeddings between models become self-embeddings. So when gamma is omega categorical, then the theory of gamma is model complete if and only if the self-embeddings preserve all first-order formulas. In other words, the automorphisms are dense in the self-embeddings. Okay, so now let's link all this. What is the? So I already mentioned two structures are homomorphically equivalent if there are homomorphisms from one to the other and vice versa. And clearly, if two structures are homomorphically equivalent, they have the same CSP. So the nice fact that we have here is every finite or countably omega categorical structure is homomorphically equivalent to a structure which is a core, simultaneously a core and model complete. Yeah? And this structure is unique up to isomorphism, and again omega categorical. So it's it makes sense to talk about the core of an omega categorical structure. And this core has very nice properties, and in the following we'll only work with structures gamma that are model complete in cores. So one nice property is that the automorphisms are now even dense in the endomorphisms. So in some sense, the unary polymorphisms are really sort of determined by the automorphisms already. So what is dense with respect to which topology? I'm always working with respect to the topology of pointwise convergence for those objects. And in this structure gamma, the orbits of n tuples are even primitive positive definable. All right. So this is the third step of the, just an example, the model complete core, for instance, of the random graph. What is it? The model complete core of the random graph. Well, the random graph contains an infinite clique. And you can certainly map the random graph to this infinite clique and the infinite clique back to the random graph, so they are homomorphic equivalent. And this infinite clique is a model complete core. The random graph is not, because it's not a core. It's model complete, but it's not a core. All right. The fourth step of the universal algebraic approach. Actually, the complexity of the CSP of an omega categorical structure, or of a finite structure, let's say first, a finite structure gamma not only depends on the polymorphism clone, but it depends on the polymorphism clone as an abstract clone. Now, what is an abstract clone? Abstract clones relate to polymorphism clones in the same way as permutation groups. No, groups relate to permutation groups. You can, if you have a permutation group, you can look at the corresponding group. If you have a function clone, which you can look at the corresponding abstract clone for it. The way to formalize it is with a multi-sorted algebra, but there are other ways of looking at it. It's basically also it's equivalent, the equational theory of the clone. And the computational complexity only depends on this equational theory of the polymorphism clone. Now, why is that? I'll not go into details here. But actually, there will be more on that in the next talk by Michael Pinsker. So I just mentioned basically the two ingredients that you need to know in order to see this. So the first ingredient is Birkhoff's theorem from universal algebra, the HSP theorem. And the second ingredient is the fact that generalizes a little bit what I've said about primitive positive definability. You can look at something more general, interpretations. What is a primitive positive interpretation? It's just a normal interpretation in model theory where you require that all formulas are primitive positive. And those primitive positive interpretations, they preserve the complexity of the CSP as well. So these two facts together, they show this. So now, this is all in the finite. I've written finite gamma. What happens for omega categorical structures? Is it again true? And can we just replace finite by omega categorical here, and that's it? And there's one twist. So as I already said, endomorphisms are equipped by the topology of pointwise convergence, the polymorphisms as well. And so these are topological objects as well. And what we have shown recently with Michael Pinsker is that for countable omega categorical structures, the complexity of CSP gamma only depends on pol gamma viewed as a topological clone. You take the abstract clone plus the topology, and this already determines the complexity. Okay. The last step of the universal algebraic approach. I'm now heading towards a more precise strengthening of the Fedder-Vardy conjecture, a conjecture which precisely predicts which CSPs are easy and which are hard. It's called the tractability conjecture. And first, I need to introduce some notions. Suppose I have two function clones, two sets of functions that are closed under composition and contain the projections. I say that this is a function from C to D. It's called a clone homomorphism if, well, the projections go to the projections. Probably I forgot to write this here. The projections have to be mapped to the projections. And, well, it's a clone homomorphism. You have to satisfy this identity for all clones in C. And then there's a special clone, very important clone, the sort of most stupid clone. It's the clone that just contains the projections. So if you have a two-element set and you look at the function clone which just contains the projections, it's a clone. But, and all of those, if your domain contains at least two elements, all clones of this type are isomorphic, and this will be called a clone of projections. Now, our most powerful tool to prove that a CSP is hard is by exhibiting a homomorphism from the polymorphism clone to the clone of projections. If you are able to do that, then we know the CSP of gamma is, oh, sorry, this should be continuously, sorry. Homomorphically and continuously maps to the clone of projections, then the CSP is NP-hard. For finite, you could, of course, omit that, but for omega categorical, you have to require continuous homomorphically maps to the clone of projections, then the CSP of gamma is NP-hard. Okay. Now, the following is a conjecture, again. It's the tractability conjecture for finite domains. I'm assuming that gamma is finite, and the rest of the talk will discuss what happens in the omega categorical. So I have a finite structure gamma, and I'm now assuming additionally that for every element of this structure gamma, there is a relation that just, a unary relation that just contains these elements. So the automorphism group of gamma will be rigid. And this assumption is basically, it's a technical assumption. You can do it. If gamma is a core, you can do this. You can add those relations, and you will not change the computational complexity. It's a basic fact. So this is a without loss of generality assumption, but it's important for the next conjecture, which is actually a theorem to a large degree. So what is this conjecture? So you have a dichotomy already. Pol of gamma has a homomorphism to the clone of projections, and the CSP of gamma is NP-hard. This is actually an immediate corollary, this last part. This is one case. And the other case is that, if this does not apply, then the polymorphism clone contains a cyclic operation. Cyclic operation is an operation which satisfies those identities. And those identities, they rule out the possibility that there's a homomorphism to the clone of projections. Yeah? If you would map this to a projection, you would violate this necessarily. If you map it to the ith projection, you would violate this identity, obviously. And actually, so far, this is a theorem. So far, this is a theorem proven by Bartow and Kozic, based on earlier work by Taylor and Bulatov. The only part which is open is that in this case, the people believe that the CSP is in P. And that's the only piece that is open. Interestingly, the algorithmic side is open here. Yeah? So we believe that we understand the sources for hardness, and the big task is to come up with algorithms in the finite. Okay. Now, what happens for omega categorical structures? Can we have a theorem of this type for omega? Can we have a dichotomy for all omega categorical structures? Similarly as here, that I would like to, and now I'll talk about this. So, because well, first of all, let me also tell you that this red part is true in many cases. For instance, if you not only have f which is cyclic, but if your f is even a majority, satisfies those identities, then the CSP is in P. If it satisfies Maltsev identities, it's true. If it's the Maltsev identity, it's true. If it's a semi-lattice operation, it's true, and so on. All right. So I want to show you that this very same approach is also useful for omega categorical structures. For some classes, this really leads to a complexity classification. For instance, for reducts of Q. So what is a reduct? You start with a structure gamma, or structure delta, sorry. And you say a relational structure gamma is a reduct of it if, well, gamma lives on the same domain, and all relations of gamma are first order definable in delta. Then gamma is a reduct of delta. So some examples, reducts of Q. So for instance, if you have all these binary relations, they are certainly definable over Q. It's a stupid reduct. Then well, this is a reduct we have already seen. It's the template for the betweenness problem. And then there are some reducts, well, that are, what is the complexity of this? What is the CSP of this? It has been studied in theoretical computer science, and here it's less obvious to see the algorithm. In fact, the CSP for this can again be solved in polynomial time. And I would like to get a classification for all reducts of Q. What is the CSP for a reduct of Q? And here we do have a complete theorem. So here also the algorithmic side is solved. So this is really now theorem complete. Let gamma be a reduct of Q. Then there are two cases again. Either there's an expansion of your reduct by finitely many constants, such that the polymorphism clone of this expansion has a continuous clone homomorphism to the projections. In this case, we know by general principles the CSP is hard. Or, if you don't have such an expansion, then you can find a binary polymorphism and automorphisms such that this identity holds. It's basically a commutative operation modulo automorphisms. And in this case, the CSP of gamma is in P, and in here actually there are various algorithms that you have to use. It's not just one algorithm that would solve it in this case, but this splits into subcases, and depending on the subcases, you have to use various tricky algorithms, solving linear equation systems over F2 many times, and actually interesting algorithms. So this is the situation for Q. And you see there's a similarity to what we've seen from the finite. But we only know it for reducts of Q. But we also know it for the reducts of the random graph. So the random graph is another very nice omega categorical structure. I'll denote it by G, vertices V, edges E. The Rado graph. Some examples of reducts. So for instance, well, I already said the random graph itself is not a core, but you could easily add a relation N, which contains all pairs of non-adjacent distinct vertices, pairs of vertices. And then this is a model complete core. Just an example, or just to give you some example of what these reducts could be, you add a ternary relation which contains all triples of elements that have an even number of edges sitting on those three vertices. And again, well, the formulation is slightly different, but again, very similar to the classifications we have seen before. Again, a dichotomy. Either the polymorphism clone has a continuous, this time without constants, just directly, a continuous clone homomorphism to the clone of projections. And by general principles, the CSP of gamma is NP hard. Or gamma has a ternary polymorphism this time, and an automorphism such that it's cyclic, a modulo, and this time only outside we apply an automorphism. It happens that it suffices here to apply outside the automorphism. And again, the CSP of gamma is in P, and again, this splits into various subcases where you have to give algorithms. But you have this interesting dichotomy. And now one could ask, can't you come up with a general conjecture that would work for all omega categorical structures? Can't you have such a dichotomy for all? And for this, I have to explain you a little bit the proof method, right, to see how far would this go. How far could we push this? And this is the connection to Ramsey theory I mentioned. So the proof method is based on canonical functions and Ramsey theory. What is a canonical function? A function from gamma to the k to gamma is called canonical if for all n tuples, t1 up to tk, if you look at the type of this n tuple that you get from applying f component-wise to the n tuples t1 up to tk, the type only depends on the types of t1 up to tk. So that's what I call canonical. And just to give you an example, if you find those multi-array functions too, this is already interesting for k equals 1. Now imagine k equals 1. You have a function, for instance, a function that maps x to minus x is canonical as a function from q to q. Because to know, you have a tuple, to know the type, right. Right, n tuples, yeah. T1 up to tk are all n tuples. This is one n tuple, this is one n tuple. So here you would have to look at n tuples again. Yeah? Here you look at an n tuple. You want to know the type of an n tuple in Q. Well, all that counts is the order, right, on those n. So if you systematically reverse the order everywhere, you only have to know the type in the preimage. All right. Two canonical functions have the same behavior if for all n tuples the image n tuples have the same type. Okay, so and why am I saying this? Because actually, if your structure is homogeneous in a finite relational language, there are only finitely many behaviors that you can have. Because to know an n-type, you actually only have to know the sub-m types where m is the maximal arity. If m is the maximal arity, you look at where are the relations. Homogeneity will imply you, will give you the type by the m subtypes. So yeah, we'll only have finitely many canonical functions, and these canonical functions are very nice to work with combinatorially. Many things like are just you can do combinatorial analysis because they're finitely many, and so let me illustrate how to apply this idea of canonical functions to classify the CSP. I'll illustrate it for Reducts of Q. So the first step is to identify some basic relations R where you know that they imply that if your polymorphisms preserve R, then they must have a homomorphism, a continuous homomorphism even to the clone of projections. For instance, this can be done for the betweenus relation. And the betweenus relation, if you look at the polymorphism clone of the betweenus relation, it will have a continuous homomorphism to the clone of projections. The second step is, well, so this will imply that the CSP is hard. So suppose these are not primitive positive definable, these relations. Right? Otherwise, we are done. If they're not primitive positive definable, there must be a polymorphism that violates it, that does not preserve this relation. And now there comes this Ramsey step. We'll apply Ramsey theory to this polymorphism to argue that we can find a canonical polymorphism that already violates the relation. Unfortunately, this is false in general. In general, we cannot do that. But, and this is an important trick that came I think, in 2011, that actually we can always do that if we add finitely many constants. Yeah? We can find this polymorphism after adding finitely many constants. All right. And this I'll expand a lot. Right, and then you look at types with respect to, it's a much richer type space than if you have these constants, and then you have enough types to really. And this step I'll expand. Yeah, this is the crucial step. This is the step where Ramsey theory comes in, and I'll expand when we can do that and when not. And then there's just one more step. There are, as I said, these canonical polymorphisms, they are combinatorially nice. You can work with them. And well, there's a certain case analysis to be done, and you use those canonical polymorphisms to somehow prove that there also exist polymorphisms that have those nice identities. And this is the most work is done here, but can be done in many cases. Interestingly, this method is not just if you hate polymorphisms and the CSP. This method also works if you're just interested in first-order reducts. Yeah? If you don't like primitive positive definitions, there's quite some work about classifying reducts up to first-order interdefinability, just determine the groups that can show up for reducts. And the same method works, surprisingly, also to do this task. And we'll see this much better in the talk of Ondra Sprungratz tomorrow, I think, who applied this for the reducts of the ordered random graph, random ordered graph. All right. So this third step, let's zoom in on this third step. But first, I need a definition of Ramsey. Luckily, my talk was scheduled after the talk of the previous talk. Solecki, Slavomir. Sorry, Slavomir Solecki. So the main difference here is now that he mainly worked in a non-structural setting, Slavomir. Yeah? Where but here I want to extend the Ramsey setting to structures that have some structure. Yeah? And so I'm writing G over H for the set of all induced substructures of G that are isomorphic to H. Yeah? I'm generalizing Ramsey's theorem to substructures and embeddings and so on. So we have this funny piece of notation here, which means that if you color the copies of P in G, you find a copy of H with two colors. You find a copy of H in G such that all copies of P in this copy have the same color. And I'm only working with two colors here, this equivalent. All right. And a class of finite structures over some signature, say a relational signature, is called a Ramsey class if for all H and P you find such a G, usually big G, and it's called a Ramsey class. All right. So an example, the class of all finite linear orders is a Ramsey class, and this is equivalent to the Ramsey's theorem itself, as explained actually in the talk of Slavomir. And a non-example, and this is unfortunate because we are interested in the random graph. In one of these classifications was for the reducts of the random graph. It's unfortunately not true that the class of all finite graphs is Ramsey in this definition. But if you linearly order the vertices of those graphs in all possible ways, the class of all linearly ordered graphs is Ramsey. And this is good enough if you're interested in reducts, because for reducts, I mean, the reducts of the random graph are in particular reducts of the ordered random, or the random ordered graph. So adding a linear order is not a big deal for our method. All right. So now comes the important canonization lemma that we use for finding canonical functions. If you have a Ramsey structure which is Ramsey. So a structure is called Ramsey, say a homogeneous structure is called Ramsey, if its H, the class of all finite structures that embed into it, if this class is Ramsey. So let's look at an omega categorical ordered Ramsey class. Ordered, I mean, I have an order in the signature, linear order. I have a function f, polymorphism, comes probably from a polymorphism or a reduct, very wild, and some constants. And this is actually already interesting if k is 1 and there are no constants. Already there, it's interesting. Then there is a function in this space. So what is this? So you take f, and you apply automorphisms at the arguments of f, and then you apply automorphism outside, and you take the topological closure in the topology of pointwise convergence. In this space, there is a function which is canonical with respect to having added the constants. All right? This is the canonization lemma. And you can either prove it by hand, by product Ramsey, or Ramsey applied many times and dealing with the constants. You can do that by hand. There's another way to prove it very elegantly using the connection of Pestov and Dodorowicz. You get this f, no, this function, no, sorry, not f. You get this function in S that you want as a fixed point of a continuous action of the automorphism group of delta on some appropriate space. But I'll not go into this now. Okay, so, but open problems. So when do we have this method? For which omega categorical structures, for which homogeneous structures in a finite language, say, can we apply this method? And that's actually questions that I have already posed in Leeds in 2011. This is the sort of two, there was Prague in between. Yeah? So the first question was, suppose I have a homogeneous structure with a finite relational language. Can we always add finitely many relations to it such that the expansion is still homogeneous, but now additionally Ramsey? Yeah. And note that this is important for the method. This would imply that our method, in principle of canonization, would apply to all homogeneous structures in a finite language, gigantically large class. Because this expansion is not a problem for our method. A variation of it, and there are many variations. So you could also ask the following, say gamma is omega categorical. Do we always have an expansion such that the expansion has still an oligomorphic automorphism group, but now it's extremely amenable? It's a variation of it. And actually, Lionel Fanté talked about precisely those two, and he made them conjectures, which makes me happy. So this would be great for the method, if this is all right. But for the CSP, there's also some caveats. So how far can we do complexity classification? There's one negative result, or non-dichotomy. Can we, for instance, homogeneous structures with finite signature? Maybe we can apply this Ramsey method always, but for the computational complexity, it's more tricky. So already in 03 with Jarek, we observed that there are homogeneous digraphs. Hansen constructed them that the CSP for this Freistel limit is undecidable. Well, it's a very simple idea. It's not. So first of all, there are many homogeneous digraphs, 2 to the omega many. And in fact, they all have different CSPs. This. Basically, those digraphs, they are described by forbidding, in an induced way, tournaments. And if the 2 structures forbid different tournaments, then you can use precisely those tournaments as instances of your CSP that show that the CSP are not the same. But on the other hand, we have only countably many Turing machines. So there are some CSPs that are undecidable. But you can do something more interesting. You can, in fact, already find in this class of Hansen digraphs structures which are in co-NP, but neither co-NP complete nor in P. A sort of co-NP intermediate, you can also do. The same I don't know how to do for NP. It's open. Huh? Yeah, that's the next slide. That's the next slide. Finitely bounded homogeneous structures. These are the structures that one would naturally work with. So what do I mean by that? I fix a set of finite structures with a finite relational signature, n, no structures, obstructions, and I look at forb of n, the class of all finite tau structures that do not embed any of the structures from n. Now, these are very natural ages for structures, and I say that the structure gamma with a finite is finitely bounded if you have if such a finite set of obstructions n exists, such that the age of this structure equals precisely the forb. And this is actually not a rare case at all. The Q, for instance, the random graph, these are all finitely bounded homogeneous structures. So what can we say here? First observation. If gamma is a reduct of a finitely bounded homogeneous structure, then it must be an NP. Yeah, because you can simply guess the expansion and then verify in polynomial time whether none of the structures n embeds. Very easy. So this is already very nice as a setting. And actually, we made the following conjecture with Michael. So we believe that reducts of homogeneous finitely bounded structures do have a computational complexity dichotomy. And I mean, this might look, if you don't, I mean, if P is different from NP, then by Lardner's theorem, there are infinitely many complexity classes between P and NP. So this is really saying something. These are not the only 2 possibilities. All right. So we have a reason to believe this, because actually it might be that we already know the border between the easy ones and the hard ones. So this is what I call generalized tractability conjecture, generalized from finite to those large class of omega categorical structures. So we have a reduct of a finitely bounded homogeneous structure delta. Assume that gamma is a model complete core. Then either there's an expansion of gamma by finitely many constants, such that the polymorphism clone of the expansion has a continuous homomorphism to the clone of projections, and that CSP is NP complete by general principles, or we have an n-ary polymorphism F, arity at least 2, and endomorphisms of gamma, such that you have a cyclic equation, but modulo applying an automorphism outside and to the arguments. Right? So this fits all, and I've only mentioned Q and the random graph, but this is also by Michael for the equivalence relation with infinite and infinite classes for examples that are related to this Boron tree. This has been verified in many instances, this type of statement, many. And in this case, we expect the CSP to be in P. All right. Open problems. This is the second part of open problems. There's one subtle point. So look at the following. We have gamma is a reduct of a finitely bounded homogeneous structure in the conjecture. We would like to assume that gamma is a model complete core, because then we can do this better. But it's not clear a priori whether the model complete core of a finitely bounded homogeneous structure is again finitely bounded. So that's a combinatorial question here for you. Another point, that's another point. Yeah, you by looking at this, you can make many interesting observations. So speculations, maybe. So you have a continuous homomorphism to the clone of projection. So this is a topological condition. This here is purely algebraic. There's no topology involved here. This is just a statement about the abstract clone. I want that there is an alpha, a beta, and an f satisfying this equation. It's purely algebraic. So is there so is it true that if you have a continuous homomorphism to the clone of projections, you also have, now if you have any homomorphism to the clone of projections, you also have a continuous one? Is this always true? And this will be the topic of Michael's talk also. Yeah? When can we get rid of the topology? When is the algebraic structure of the clone determining the topology? This will be Michael's talk. And finally, I already mentioned that. Yeah, suppose your CSP is in NP for an omega categorical structure. Is it always NP complete or NP? Just very basic questions open in this. All right. Thank you very much. Right. It's a union space, and for each arity, you take the right. Yeah. Sorry.
For the forbidden tournament intermediate co-and-and with Griffith, can you say something about the tournaments? Is there some way of describing?
So the first thing that we observed is that if you forbid all the tournaments that Hansen described, Hansen gave an infinite list of tournaments, which had the property that none of them embeds into another. Like with respect to embedding, it's an anti-chain. And then he says, okay, I take an arbitrary subset of this anti-chain, I forbid it, and it will always give me a different Fraisse limit. So now, if you look at the CSP where you forbid all these tournaments, it's already co-NP complete. Okay, happens to be like that. And then you basically do Lardner's proof, Lardner constructed complexity classes between NP complete and P by a very slow diagonalization, very involved. And basically, we do the same proof by actually shooting holes into the obstruction sets. We forbid the right amount of tournaments to fall into this region. That's the proof.